Okay, now let's recall. Oops. Recall. Suppose we have a vector space V over the real numbers, say, and let's suppose we have a basis V1, V2, Vp of V. Then for any vector V in V, hold on. Maybe let me call it W instead. For any vector W in V, there exists unique W1, W2, WP real numbers such that W is the linear combination of V's with coefficients being these little w's. So W1 V1 plus W2 V2 plus WP VP. Okay. And this defines a one-to-one correspondence between the vectors in V and the p tuple of real numbers, these little w's. All right. So for every w can correspond to a p tuple, W1, W2, WP. And this is denoted by W bracket B, and this is an element in RP. Okay. So as we mentioned last time, this is called a coordinate vector. Coordinate vector of W with respect to the basis B. Okay. So the point is this correspondence or identification gives a way to view and identify V with RP, right? Because the one-to-one correspondence, exactly identifies every element in V with an element in RP. So we would like, to further, and so we would like to sort of understand how the vector space structure is identified under this correspondence. So furthermore, and the statement is that this correspondence also identifies the vector space structure. Okay, to be more precise, we can make the following theorem. Again, we have V a vector space and B a basis. So suppose I have U and W, both vectors in V, and say C is a real number. Then two things happen. Having u and w means that I can form u plus w. That's a vector in V, so I can ask for its coordinate vector, and that will turn out to be the coordinate vector of u plus the coordinate vector of w. Okay, and also having u and having c, I can consider the scalar multiplication cu, that's a vector in V, so I can ask for its coordinate vector with respect to B, and that turned out to be the coordinate vector of u times c. Okay. Now proof. The proof is fairly simple-minded. You got two equalities to prove. So what you do is you compute both sides. So say first of all, to determine the coordinate vectors for u and w, I have to write them as linear combinations of the v's. So say u is u1 v1 plus u2 v2 plus plus up vp, where the u's belong to R, and similarly for w is w1 v1, w2 v2, wp vp, with all these w's in R. Okay, suppose that's true. Then, first of all, you can now compute u plus w by simply adding these two linear combinations. And then the next thing to do is to write this sum here as a linear combination of the v's. And we've done things like these several times before, so we will be fairly quick. We just collect the terms proportional to the same basis vector and do that. Okay. Okay, so what this tells you is that the coordinate vector for u plus w with respect to B can now be read off from this as the coefficient of this linear combination. All right, so this is the coordinate vector for u plus w with respect to B. And of course, this can be written as a sum of two vectors in Rp, one with entries being the u's, the other with entries being the w's. And so when we write u and w as linear combinations of the v's, we've already found out about their coordinate vectors. All right, so this is the vector with entries being the u's is the coordinate vector of u. The vectors with entries being the w's is the coordinate vector for w. So therefore, what I have here is the coordinate vector of u plus the coordinate vector of w. That's what I want to prove, one of them. Now, for the other equality, I have to know the coordinate vector for c times u, and that's easily computed by multiplying c to the linear combination that gives us U. And then distribute the multiplication to each term. Like that. So, and this immediately tells us that the coordinate vector for CU is this column vector with entry CU1, CU2 up to CUP. And of course, by the way the scalar multiplication is defined for vectors in RP, this is the scalar C times the vector U1, U2 down to UP. And that vector is the coordinate vector for U. So this is C times the coordinate vector of U, which is what we want. Okay. So something else. So now we now this theorem, as we mentioned, is telling us that the correspondence between vectors and its coordinate vectors identifies the vector space structure. And that is, it identifies the vector space V with the vector space RP in a particular way. And this identification can be used for studying property stuff about the vector space V. Okay, so that was something about the vector space of V. Okay, so let's formulate some theorem for that. Again, let's recall that the setup is you have a vector space over R, and B is a basis consisting of V1 through Vp. Okay. And now suppose I have a subset or a bunch of vectors from V. Say U1 to UM. Okay. And yeah. Okay. So this, once we have S, this collection of vectors, we get its span. The span of S, which is the same as the span of these U's, U1, UM. Okay. So we then have the following statements. A vector U is in the span of S if and only if its coordinate vector with respect to a basis B is in the span of the coordinate vectors of the U1s, U2, and so on. Okay. Right. Sometimes we would like to know whether a given vector is in the span or not, and this is telling us that we can check this after passing through the identification and do this in RP. 2. The set S is linearly independent if and only if the set, namely its coordinate vectors U1, the coordinate vectors for U1 through UM is linearly independent. Okay. Prove. Okay, let's see how do we prove this. Well, the first one, when we have this U, to say that it belongs to S, sorry, the span of S, or in other words, the span of U1 to UM is the same as saying that U is a linear combination of the little u's, like U1 through UM, right? So U belongs to the span if and only if U is equal to, say, A1 U1 plus A2 U2 plus stuff plus AM UM for some A1 through AM in real numbers. Okay. And now this is equivalent. This is the same as saying that, oops. This is the same as saying that the coordinate vector of U is the same as the linear combination of the coordinate vectors of the U1s through UN, M. So, like that. Here we've used the previous theorem. Okay, to rewrite the right-hand side like this. But when you have an equation like this, it tells you it's equivalent to say that the coordinate vector of U belongs to the span of the coordinate vectors of U1 and up to UM. Okay. All right, that's that. Now for the part 2, to say that this collection U1 through UM is linearly independent, if and only if whenever A1 U1 plus A2 U2 plus up to AM UM is equal to 0 for whenever this equation happens, we must have A1 equals to A2 equals to stuff equals to AM equals to 0. Okay, that is the only linear combination of the U's to equal to the 0 vector is the trivial one. Now, this is the same thing as saying whenever the coordinate vectors, because remember there's a bijective correspondence between vectors in V and its coordinate vectors. This is to say that whenever you have an equation like these, we must have the A's being O0. M equaling 0, which is the same thing as saying that these vectors, U1, the coordinate vectors of the U1 through UM, these guys are linearly independent. Okay. All right, so that's that. Now, there's a corollary that we can consider here. That is, again, in the same setting as above. In the above setting, if we have a basis, well, we already have a basis. Let's say again S. Sorry, not S. Just do U1 through UM. This is a basis of V if and only if the collection of its coordinate vectors, which is now a subset of RP, is a basis of RP. Okay. And proof is fairly straightforward, so let me not talk about it. But instead, let's use this theorem in some examples. Let's consider once again the space of polynomials P2, and we've seen a basis before, 1x squared in P2 is a basis, right? And let's consider another collection, 1 plus x, 1 plus 2x plus 1x squared. Okay. Now I want to understand whether this is a basis or not. So the question is this a basis? And we're gonna use the corollary we just saw to study this question, right? By definition, to verify whether you have a basis or not, you have to check whether it's linearly independent or not, or whether it does spans or not, right? So the corollary above, this corollary would allow us to study this question, or rather by transferring the question to vector spaces in the RP or the Rn vector space. So for that, we pick a reference basis, which is the one consisting of the monomials B. And to proceed, we have to first determine the coordinate vectors of these three vectors with respect to B. Now for 1, it's just 1, 0, 0. 1 plus x is 1, 1, 0, right? Because it's 1 plus x. 1 plus 2x plus x squared has coordinate vector being 1, 2, 1. Oops. Okay. All right. So now, the question now is transferred or translated into the following question about vectors, about the vector space R3. Is this collection of three vectors a basis? And the answer is immediately yes. Maybe with some details. Let's see. So spanning, we need to check two things, right? First of these vectors must span R3. So if I have a vector say B1, B2, B3 in R3. I want to be able to write this as a linear combination of the three basis vectors, the three vectors that we would like to be the basis. Okay. So what is this? This is and you can recognize this as a system of linear equations immediately. It's x1 plus x2 plus x3, x2 plus 2x3, and x3. So you want to determine x1, x2, and x3, and this is now a linear system with three unknowns, the x's, and three equations. I mean, you certainly have the usual approach of reducing the augmented matrix into reduced echelon form and go from there. But for this example, it's fairly easy to solve because x3 is given to us. x3 has to equal to b3. x3 is b3, right? Now, when you have x3, you can use the equation above it to solve for x2. That will give you x2 equals to b2 minus 2, well, x3, so that was b2 minus 2, b3. Okay, and finally, you have this equation. The first equation you can use to solve for x1. X1 is b1 minus x2, so that's b2 minus 2, b3 minus x3, which is b3. And you can further simplify this expression, but what we need to know from this is that you have a solution for the x's. So this b belongs to the span of the three vectors. Right? Moreover, linearly independent. Right? To be a basis, we need these three vectors to be linearly independent. So for that, we have to consider the linear combinations and set it equal to 0 and solve for the x's. But we've already done that as a special case of the previous study, right? We just want the b's to be all 0 in this equation. And if you have, we've already solved for the solutions in general. Now, if we look at this solution here and set all the b's to 0, you'll see that means all the x's are 0. x1 equals x2 equals x3 equals to 0. So linearly independent. Okay, and that tells us that these three vectors, these three coordinate vectors, indeed form a basis of R3. And by the corollary we just discussed, the vectors in P2, that is 1 plus x and 1 plus 2x plus x squared, form a basis of P2. Okay. Let's see here now. Okay, so let's consider some perhaps more complicated example. This is one example. Let's do another example. So P4, first of all, P4 is the space of 4 degree at most 4 polynomials. So they are of this form. With all the coefficients being in reals. And first of all, I claim that P4 has the following bases consisting of monomials. And that's easy to check. Certainly, it's easy to see that they span. And it's also it's a bit tedious, but it's also not hard to check that they're linearly independent. Now, let's consider the following collection of vectors: x4, 3x3, 2x4, x3 minus x squared plus 5x plus 1. Let's see, x4 plus x plus 3, x4 plus x3 minus x plus 2, and x4 plus x2, right? All these are vectors in P4. Let's give them some names: P1, P2, P3, P4, and P5. And the question we can ask is that, are we getting a basis here? And just like the previous example, the idea here is to use the corollary to translate the question into a question about, in this case, R5. Let's call the reference basis the monomial basis by the name B. Then we can write the coordinate vectors of these P's as follows: 4, 2, 0, 3, 1. P2, B is 1, 5, minus 1, 1, 0. P3, B is 3, 1, 0, 0, 1. P4, B is 2, minus 1, 0, 1, 1. And finally, P5, B is 0, 0, 1, 0, 1. Okay. So we have 5 vectors, all of them in R5. We know that R5 is 5-dimensional, so it certainly seems hopeful that there could be a basis. So all we have to do is decide on whether one of the two conditions, right? Being a basis requires 2 things. It's either it's linearly independent and it spans. But if we have the right number of elements in our basis, that is, the number has to be equal to the dimension of the vector space, then we only need to check one of the 2 conditions. So let's check whether it's linearly independent. And for that, we're going to skip some steps, right? Because we can view these as column vectors of the following 5 by 5 matrix. Okay, so and what do we need to do? All we have to do, we are asked to do, all we have to do now is to decide whether this matrix is non-singular or not, and that can be determined basically in the most basic way by row operations. Okay, we're gonna try to turn it into reduced row echelon form, and we're gonna skip the details here, but simply tells you that the end result, that is the reduced echelon form, is this one. So non-singular, hence yes, it is linearly independent. And because you have 5 linearly independent vectors in R5, it's a basis. Okay, very well. So that's that. And now let's continue some abstract discussion. Suppose we have a vector space over some scalar field K, and if V has a basis, I may V1 say to Vn of, and this basis has n vectors, then V is n dimensional. Okay, and the notation is the dimension of V is n. It is also possible if V is not trivial and does not have a basis, consisting of finitely many vectors, then V is called infinite dimensional. Infinite dimensional. Okay. And right, so this is just a definition. When you have a basis, the number of elements in a basis is called the dimension. If you don't have a basis that has finitely many elements in it, it's called infinite dimensional. And note, one thing that we should have said before, that a single element vector space consisting of just the zero vector is a vector space. And its dimension is 0. Okay, that's one thing to say. And of course, for the first definition here to make sense, it is implicit. It is implicitly required that any two bases of the same vector space V must have the same number of elements. And we prove something like this for subspaces of Rn. And in this abstract setting, the proof is actually the same. So we will not spend much time on this. Now, what I really want to emphasize or demonstrate is an example of the second case. That is, it is possible in this abstract setting of vector spaces for it to be infinite dimensional. So example, right, remember the vector space of continuous functions from a closed interval AB to the real. Okay, and this space, this is a real vector space. This is infinite dimensional. Okay, and to see this, how do we proceed in order to see this? We need to demonstrate that we're not gonna have a basis consisting of finitely many elements, right? The point is finitely many. So all we have to do is exhibit an arbitrarily long sequence of vectors that are linearly independent. And that's easy to do. Now, if you consider monomials 1x, x squared up to x to the n, we can easily check that this is linearly independent. For any n. Okay. And certainly these functions, these monomials viewed as functions belong to CAB. Each of these belongs to CAB, right? So what this tells us is that you have an arbitrarily long sequence, arbitrary being that the same statement holds true for any n. You have an arbitrarily long sequence of linearly independent vectors in this space of continuous functions. So there's no way that it has a finitely many. There's no way that it has a basis consisting of finitely many elements. Okay. So, like I said, this example shows that it is possible in this abstract setting of vector spaces for a vector space to be infinite dimensional, and that the discussion about infinite dimensional vector space is not really what we can do here in this course. So we will just proceed to discuss some properties of dimension. And basically we have the same, we've seen some properties of dimensions of subspaces of Rn, and the same properties hold here in this abstract setting. Suppose V is a vector space over a field K, and let's assume that its dimension is P. Then any set of at least P plus 1 vectors in V is linearly dependent to any set of P linearly independent vectors in V is a basis. And we will skip the proof of these because we've demonstrated that for finite, once you have a basis, you can translate the problems about V into the problems about Rn or Rp in this case. And we proved things about Rp before. So we will just not worry about them. And furthermore, you have also again have some other properties. A spanning set of if V is p-dimensional, a spanning set of V must have at least p elements, p vectors. Okay. Again, to prove this, you translate the problem back to Rn or Rp. And finally, any set of p vectors that span V, spans V is a basis. Okay. All right. So again, we will not prove this because again, the proof can be done by translating the problem back to Rp when you after choosing a basis. Okay, so now let's see. Now we've done quite some discussion for this sort of abstract vector spaces. Now the next topic is about going back to Rn again. So perhaps it is a good place to stop.